Okay, welcome back to another training session for the Singapore Junior Chemistry Olympiad. So this training session, we are going to finish introduction to organic chem, and then we will move on to alkanes and alkenes. All right, so intro to organic chem is set number 7. We will start from page 11, which is the fractional distillation of crude oil. So if you recall the last lesson, we spoke about organic compounds. Organic compounds are made up of carbon atoms and other elements. All right. An important group of organic compounds is hydrocarbons. So hydrocarbons are compounds that contain hydrogen and carbon atoms only. So hydrocarbons are organic compounds containing hydrogen and carbon atoms only. All right. The keyword here is only. So it only has hydrogen and carbon atoms, no other elements. So no oxygen, no chlorine. All right. Now, where do hydrocarbons actually come from? Now, hydrocarbons are found underground, under the sea as well, as a mixture called crude oil. Now, crude oil is also known as petroleum. All right, so we have to drill for crude oil from underneath the ground, underneath the sea. Now, crude oil is a fossil fuel mixture which is formed by the action of Earth's intense heat and pressure on the fossils of dead plants and animals, and is mined out of the ground through wells and drills. Now, this is what the well looks like, the oil drilling well looks like. There's actually a drilling part that goes under the ground, under the sea. And when it goes under the sea, it hits the petroleum. Petroleum is crude oil. Same thing. All right. Now, above the petroleum, very often you find a gaseous mixture called natural gas. Now, natural gas is mainly methane. And methane has the chemical formula CH4. All right, so you may have just learned methane in class as well for the Sec 3 students. Methane's dot and cross diagram looks like this. Okay, I'm showing just the outermost electrons. Okay, CH4. Okay, so this is the dot and cross diagram for methane, CH4, showing just the valence electrons. Now, natural gas is mostly made up of methane. Now, petroleum is another useful part. The crude oil part is useful, but crude oil on its own is a mixture, it's impure. So on its own, it's not super useful yet. We need to purify and separate the hydrocarbons in crude oil. So which method do we use? We will make use of fractional distillation to separate the hydrocarbons in crude oil, because the hydrocarbons in crude oil are miscible and have different boiling points. So for both the Sec 3 and the Sec 4 students, this should be revision for you. You learned fractional distillation under separation techniques. All right. Okay, so fractional distillation is a suitable method for separating mixtures where the substances are miscible and have different boiling points. Miscible means they can be mixed together. Okay, now the hydrocarbons in crude oil have different boiling points, as we will see shortly. So fractional distillation is the method to separate crude oil. What does it look like? It looks like this. All right, petroleum is a source of energy and is separated by fractional distillation. Now, how does it actually work? Let's go through the 3 steps. The first step is where the liquid crude oil, the liquid petroleum gas, is heated in a furnace until it turns into a vapor. All right, so that's the first important step. The liquid petroleum is heated in the furnace until it turns into vapor. Okay. So that's step number 1 that you actually see on your notes. All right. Now, step number 2 is where the vapor moves up into the fractionating column. So if you recall, fractional distillation requires a fractionating column. All right. Now, the key thing is, as the vapor moves into the fractionating column, the vapor will start moving up. The vapor will rise up. All right. Now, as the vapor rises up, it will cool down. So different fractions of the petroleum mixture will cool down and be condensed. So it is condensed at its boiling point. And because they have different boiling points, they are collected at different points in the fractionating column. All right, so that's how the separation works based on the boiling point. So just give me a minute. I think the OneNote is still loading. All right, my annotations. Okay, so just let me pause the recording first while I try to work out the OneNote and let it sync. All right, thanks for waiting. I've solved the technical difficulties. So now we are still on page 12 of set number 7. This is Intro to Organic Chem, the fractional distillation of crude oil. All right, so as mentioned, fractional distillation is used to separate crude oil into its hydrocarbons. Now, the first step is the liquid crude oil, petroleum, is heated in a furnace until it turns into a gas, a vapor. Now, the vapor will enter the fractionating column and move up. As it moves up, the vapor will start to cool down. All right. And we have just seen they have different boiling points. This means that they will start to condense, but at different points in the column, because they will condense based on their different boiling points. Okay. Now, the fractions which have smaller hydrocarbons with fewer carbon atoms have lower boiling points. So this is actually a pattern you should learn. Smaller, fewer atoms, lower boiling points. Now, this will be very helpful as well when you look at molecules with a simple molecular structure. Now, you will have learned in chemical bonding that simple molecular structures often result in a low boiling point. That is because of the weak intermolecular forces of attraction between molecules, which require very little energy to overcome. But there is also a pattern amongst the simple molecules. If the simple molecules are smaller, they have fewer atoms, and they are lighter in mass, their boiling points are lower. So for example, you compare hydrogen gas, H2, versus something like sulfur dioxide, SO2. H2 is much smaller, it has fewer atoms, a smaller mass as well. That's why H2 has a lower boiling point. On the other hand, sulfur dioxide is SO2. It is bigger, it has more atoms. As a result of that, it has a heavier mass and also a higher boiling point than hydrogen gas. All right, so amongst the simple molecules, the size, the number of atoms, and the molecular mass tells you roughly what its boiling point is going to be compared to other simple molecules. All right, so in this case, we are talking about hydrocarbons, organic compounds that contain hydrogen and carbon only. So smaller hydrocarbons have fewer carbon atoms, therefore they are lower boiling points, and they'll be collected at the very top of the fractionating column. All right. On the other hand, fractions with larger hydrocarbons with more carbon atoms will have a higher boiling point, and they are collected at the bottom of the fractionating column. All right. Now the fractions have names. You should try to learn the order of the fractions. So the one on top is called petroleum gas. Then we have petrol, we have naphtha. Okay, we also have kerosene. Okay, so up to this stage, I'll try to copy down. Now, kerosene has a separate name. It's also called paraffin. Right? Now, paraffin oil, kerosene oil, is what we commonly use as a fuel for aircraft, aeroplanes. But besides that, paraffin oil is often used to make candles as well. Below that, we will have diesel oil. Lubricating oil. And finally, the last one at the bottom, bitumen. So these are the names of the fractions in the fractional distillation of crude oil. What it means is that crude oil can be separated by fractional distillation into these fractions. All right. So maybe you can just take down the names of the fractions first and give me a thumbs up once you're done. Okay, thank you, Kyla. Okay, the other 3 students, I'll be done. Okay, with the copying. Okay, just let me move on from here. So these are the fractions that are obtained after fractional distillation of crude oil. Okay, now if you notice, I've given you the boiling points of the fractions there. All the boiling points, you can notice lowest boiling point on top, highest boiling point right at the bottom of the fractionating column, right? The next thing you notice is the boiling points given to you, they are all as a range, right? They are all quoted as a range. They are never quoted as a single fixed temperature. So what it means is that the melting point, boiling point and melting point in this case are not fixed. Because you can see a range, this means the boiling point is not fixed. So when will a substance have a boiling point that's not fixed? This means that each fraction is still a mixture. All right, each fraction is still impure. Then you must be wondering, hey, the whole purpose of fractional distillation was to separate crude oil. So at the end of the day, we still end up with something that is not pure? Yes, each fraction is still a mixture of hydrocarbons. It's not pure. However, the fractional distillation has allowed us to separate and purify it to some extent, to a certain extent, such that each fraction is now sufficiently separated to allow it to be sold for a particular purpose. For example, after you separate crude oil, you get petrol. Petrol is one of the fractions. Petrol is very useful. It can be sold as a fuel for cars. Similarly, kerosene is a fraction from the fractional distillation of crude oil. Kerosene can be sold as a fuel for aeroplanes, aircraft. All right. Now, so why is fractional distillation suitable? We have just covered that. It's suitable because the hydrocarbons have different boiling points and are miscible. Okay. Now, going on to the next page, you can tell that the fractions are all mixtures because they have a range of boiling points. Right? So we have seen that smaller fractions are shorter and have fewer carbon atoms. They have lower boiling points and they're collected nearer the top. On the other hand, larger, heavier fractions consist of longer hydrocarbons with more carbon atoms. They have higher boiling points and are collected nearer the bottom of the fractionating column. All right. Ken? Now you have to learn the uses of the petroleum fractions, the fractions of crude oil. So please have a read through some of their uses. Their uses are all listed here. You notice that every single fraction has a different use. Importantly, the uses are based on the flammability. Generally speaking, lighter fractions with fewer carbon atoms are more flammable. So the lighter fractions tend to be used as fuels because they are more flammable. The heavier fractions are thick and viscous, so they are less flammable. So the heavier fractions like lubricating oil, they are not usually used as fuel. All right, bitumen not used as fuel. Now, so how to remember the order of petroleum fractions? I think I've given this to you. It's a simple mnemonic to help you remember the order of the fractions from top to bottom. All right. Now, the next part is, of course, how do we convert the bigger hydrocarbons into smaller ones? If you notice, we just said the larger fractions are heavier, they are very thick and are less flammable. So they are not so useful because they tend to undergo what we call incomplete combustion. Incomplete combustion produces carbon monoxide, which is CO, and a lot of soot. All right. So this is not very useful, right? That means it will burn, but it doesn't burn very well. It's not very flammable. We want things that are more flammable. This means that smaller hydrocarbons are more in demand. They have higher demand. So we try to convert the larger hydrocarbons into smaller ones. And this reaction is called cracking. Cracking is the reaction that converts larger hydrocarbons into smaller ones. And this is the equation shown below. For cracking to occur, you will need a catalyst. The catalyst is aluminum oxide or silicon dioxide. Now, catalyst is a substance. It's a chemical substance that is added to speed up a chemical reaction. So we add in silicon dioxide or aluminum oxide to speed up the chemical reaction. So what this does is it speeds up the breakdown, the conversion of larger hydrocarbons to smaller hydrocarbons. Now it needs aluminum oxide and silicon dioxide catalyst. All right, it needs both. Okay, sorry, it needs either one, aluminum oxide or silicon dioxide. But it needs both a catalyst and a high temperature of 600 degrees Celsius. All right. So this is what a setup looks like. Now, you notice I've given you an equation over there. This is an example equation, okay? C12H26. This is a large hydrocarbon. You want to convert it to a smaller one. So how do you find the missing dotted product? Now, you notice that this is all about balancing chemical equations, which you have done in class with your teachers. The idea behind balancing a chemical equation is that you must ensure that the number of carbon atoms is the same. The number of hydrogen atoms must also be the same on the left and on the right. So now let's attempt to count. We are going to use green color to highlight the carbon. Right? So over here, there are 12 carbons. But over here, in 2C5H10, we have 10 carbon. 2 times 10. 2 times 5 equals 10, sorry. So how many carbons do we have? We need to have 2 carbons in the missing product. So it's C2, 2 carbons. Next, we go to hydrogen. There are 26 hydrogens on the left. How many hydrogens are there on the right? Well, over here, we have 20 hydrogens because it's 2 times 10, right? 2 times 10 equals 20. It's 2C5H10. So it's 20. Over here, don't forget your H2. H2 is hydrogen gas, right? H2 has 2 hydrogens. So you count now, okay, I got 26 hydrogens on the left. On the right-hand side, I have 20 plus 2, 22. That means my product must have 4 more hydrogens to balance out the equation. Therefore, the missing dotted product is C2H4. Okay? Now, this is how you find the missing product by balancing the chemical equation using the concept that the number of atoms on both sides of the equation must be the same. Okay? So that's it for cracking. So if you are done copying this page, can you please give me a thumbs up so I know I can move on? Okay, so this is the same concept that you have been doing with your teacher so far, balancing chemical equations. Okay? All right, so that's the end of Intro to Organic Chem set number 7. So after this, let's move to set number 8, which is entitled Alkanes. So we are going to begin studying the first homologous series, alkanes, and its reactions. All right. Okay, so now let's move to alkanes. So you should have received this set of notes from your teachers, okay, set 8 alkanes. But if you don't have this set of notes with you right now, you can also refer to the Chemistry Olympiad 2023 class notebook to get a copy of these notes in soft copy. All right. Now, for organic chemistry, I like to summarize everything you need to know on the first page. So these are the summary for alkanes. Now, for every single homologous series, if you recall last session, we spoke about homologous series. It's a family of organic compounds. So alkanes are a family of organic compounds, which have certain similarities. First, you will need to know that all alkanes follow this general formula. The general formula is the one with N inside it. So the general formula of alkanes is CnH2n plus 2. What is N? N is the number of carbon atoms. So how many carbon atoms you have in the alkane, you just sub in. For example, if I have 10 carbon atoms, I sub in C10H2 times 10 plus 2. So C10H22. All right. Now, alkanes are described as saturated hydrocarbons. Saturated means, in organic chemistry, saturated means no carbon-carbon double bonds. So no bonds like this. All right. So saturated means no carbon-carbon double bonds. So alkanes only have single bonds between the carbon atoms. Next, we move on to the trends in physical properties. Now, this one is the same for all the homologous series. For the physical properties, as the number of carbon atoms increases, the flammability goes down. However, the viscosity, how sticky it is, goes up. So larger alkanes are more viscous. Larger alkanes also have a higher melting and boiling point. Okay. Now, so these are the physical properties. Flammability decreases, viscosity increases, melting and boiling points also increases based on the number of carbon atoms increasing. All right. From the physical properties, we will move to the chemical reactions. So alkanes starts with, that name got ane inside, ACS. Alkanes undergo combustion and substitution. So we will look at these two reactions in greater detail later on as we go through the notes. All right, so this is a quick summary that you can return to whenever you are dealing with the alkanes and you're not sure. Okay, the structure and naming of alkanes. Now, alkane homologous series, as said just now, the general formula is CnH2n plus 2, where n is the number of carbon atoms. All right. Now, alkanes have no functional group. This means that alkanes do not have a unique bond, a unique atom, or a unique group of atoms that gives its unique chemical properties. All right. Alkanes is the most basic, don't have any unique functional group. Now, alkanes, we said just now, are saturated because they contain only carbon-carbon single bonds. And importantly, they are saturated because they do not have carbon-carbon double bonds. All right. So from this, we understand a little bit more about alkane homologous series. They are saturated. They follow the general formula CnH2n plus 2. In the terms of the naming, we have learned last lesson under Intro to Organic Chem. The number of carbon atoms determines the prefix that it would use. Right? 1 carbon is meth. 4 carbons bute. That's why it's butane. 5 carbons pent, pentane. So you realize the prefix, the first part of the name, follows the number of carbon atoms. The second part of the name, ane, A-N-E, tells you it's an alkane. All right? So we have a few missing blanks there. 2 carbon atoms, 2 is F. So it's ethane. 3, the prefix is propane. Okay, so that fills up the 2 names of the alkanes there. Next, we move to the molecular formula. We need to make use of the general formula, CnH2n plus 2. Then we need to sub in n, where n is the number of carbon, right? So we sub in C1H2 times 1 plus 2, so 4, CH4. So methane, the one you learn under chemical bonding, is CH4. You can quickly work out the rest. If I sub in n equals to 4, C4H, 2 times 4 plus 2 equals 10, C4H10. C5H12, C6H14, C7H16, finally C8H18. All right, so you just have to sub in n correctly, where n is the number of carbon atoms. Next, the structure of the alkanes. So we can draw the structural formula of the first 4 members of the alkane homologous series. So what is draw structural formula? Structural formula is like this, where you represent the covalent bonds with lines. So these are all single bonds, so it's single lines. So in methane, it's CH4. Okay, it's joined to the hydrogen by single bonds. Now, ethane has 2 carbons. You always draw the carbon first. You know it's alkane because the name ends with A-N-E. So it's a single bond only. It doesn't have any other types of bonds, right? It only has single bonds. The next concept is that you need to know each carbon must be surrounded by 4 bonds. So you must ensure that every single carbon atom in the alkane has 4 lines around itself. And you fill up those lines with hydrogen. And that's why ethane is C2H6. Next, propane. 3 carbons. Again, you know that it has no functional group, so no double bonds, no other atoms, except hydrogens and carbons. You make sure that every single carbon has 4 bonds around itself. So this is C3H8. The structural formula of propane is as such. Okay, finally, we move to butane. 4 carbons. So I always draw my carbon atoms out first. If I know that but means 4 carbons, I draw 4 carbons out. It's single bonding. All right. Next, your task is to ensure that every carbon has 4 bonds. So make sure that every carbon has 4 bonds. Count properly. and you are done, right? Drawing this is straightforward. So it's C4H10. All right, so we have drawn ethane, propane, and butane. So once you're done copying, can you please give me a thumbs up so that I know you have done with this? For those with the notes, for those without the notes, of course, you can use a piece of paper as well to work this through. Okay, great. Now let's look closely at C4H10. So you notice that Mr. So has drawn the butane molecule with the 4 carbons in a straight line. So we say that butane is what we call straight chain. This is a straight chain because the 4 carbon atoms have been arranged in a straight line. But the reality is this the only way to draw something with C4H10? The answer is no. All right. We could have drawn the 4 carbons in a straight line like what I have just done, but I could also have drawn 3 carbons in a straight line with 1 other carbon sticking out at the side. This is called a side chain. I could have drawn 1 carbon sticking out at the side, right? So these two both have molecular formula C4H10. So we say that they have the same molecular formula, but different structural formula. Same molecular formula, in this case, C4H10. But the structural formula is different. Why is the structure different? Because it has a side chain. Okay, so these two molecules that you see on the bottom, they are not the same. They are known as isomers of each other because one of them is a straight carbon chain, the other one has a side chain. Okay, so the first one we will call it butane, but the second one we are not going to call it butane. Why? Because the longest continuous carbon chain only has 3 atoms. The longest chain only has 3 carbon atoms, right? So it's not butane, it's propane. But clearly it's not just propane, it has a side chain. The side chain is an alkyl group. The side chain has only 1 carbon. So we say methyl propane. Okay, so it's methyl because the side chain is a CH3 side chain. Okay, methyl is called CH3. So this is methyl propane. Now, isomers like butane and methyl propane, they will have different physical properties. The most common one is melting and boiling point. You can clearly see the boiling point which is given to you for butane and methyl propane are not the same. All right, so isomers will have different physical properties. Now you notice Mr. So has used the word longest continuous carbon chain. How do you know if something is the longest continuous carbon chain? It is the longest and continuous chain that you can highlight without lifting your highlighter from the paper. So I advise you to try highlighting the carbon chain without lifting up your highlighter. That is the longest continuous chain. So no matter how you try, for methyl propane, the longest continuous carbon chain is 3 carbon atoms. Okay? Now moving on to the next page is practice on isomerism. So now we are dealing with something bigger, C5H12, but the principle is the same. I start off with 5 carbons straight chain. I make sure everything has 4 bonds around itself. Every carbon must be well taken care of with 4 bonds around itself. And so this is C5H12. It's straight chain. When it's straight chain, we just call it pentane. So pentane, like butane just now, is straight chain. Okay. However, clearly, this is not the only way to draw a hydrocarbon with molecular formula C5H12. Mr. So could think of, how about I just put 4 of the carbons in one straight line? Then I have one side chain like this. This also works, right? This is a branch chain with a side group. Then I just have to continue and make sure that every carbon atom has 4 bonds around itself, including my side chain. This one you count properly, also has 5 carbon, 12 hydrogen, right? So it's still C5H12. But now this is not pentane. You have to now draw this isomer and try to highlight what is the longest continuous carbon chain. Remember, longest and continuous means you take your highlighter, you highlight without lifting your highlighter up from the paper. If you do that, you realize, oh, the longest chain only has 4 carbon atoms. Therefore, this is called butane. But clearly, it's not just butane. There is a CH3 side group, right? There's a CH3 here. So just now we saw CH3. CH3 is called methyl. So this is methyl butane. All right. So what Mr. So has drawn in part 2 is a branched isomer. Branched, because it has a side group. It's a branched isomer called methyl butane. Okay. Now for part 3 and part 4, can propane have isomers? The answer is no. All right. Propane doesn't have isomers. If you were to arrange the 3 carbon atoms, there is really only one way to do it. All right. Any other way will result in the same molecule being formed. You notice when I put the methyl group, it cannot be the carbon atom at the end. It must be the carbon atom somewhere in the middle. Okay. So propane doesn't have isomers. Now, I shall leave you to do part 4 yourself. Try drawing out all the different isomers you can find for hexane. Later on, you can check the OneNote for the answers. Now, let's go on to the chemical reactions. So, you can see the next page is still on physical properties. The trends in physical properties. For example, flammability goes down, viscosity goes up, melting point goes up. These properties and the explanations, I shall leave you to read it on your own because I want to move on to the chemical reactions of alkanes now. Now, the chemical reactions of alkanes, as I mentioned, A, C, S. Alkanes undergo combustion reactions. Alkanes also undergo substitution reactions. So let's go with the first one, combustion. Now, combustion requires oxygen, meaning in the equation, you should see something, something, something plus O2 forms CO2 plus H2O. If the combustion is complete, you will produce water and carbon dioxide only. All right. Now, complete combustion occurs when oxygen is in excess. This means I have a large amount, a lot of oxygen is available for combustion. That's why it's complete. That's why you form CO2, so much oxygen, right? However, the reverse of complete combustion may happen, and this occurs for incomplete combustion. When the combustion is incomplete, that's when oxygen is limiting. That means a small amount of oxygen. A limited supply of oxygen results in incomplete combustion. Now, the products of incomplete combustion are water, carbon monoxide, or soot. Okay? Now, we will focus on how to write and balance the chemical equations for complete combustion. So the idea is you need to know CH4 plus O2 is complete, so it forms CO2 and H2O. Obviously, this equation is not yet balanced. You must count the number of carbon. 1 carbon on each side. So carbon is all right, it's balanced. However, next you look at hydrogen. I have 4 hydrogens on the left, only 2 on the right. Therefore, I need 2 H2O to balance this equation. Next, the last part you count oxygen. 2 and another 2. 2 plus 2 equals to 4 oxygen atoms, which means that in terms of O2, I will need 2 O2. By having 2 O2, you basically form 4 oxygen atoms. Okay? So remember the order in which we just counted. We counted carbon first. Balance carbon with CO2. Once carbon is done, next step, step 2, hydrogen. Balance it with water. The final step is to total up the oxygen and balance oxygen. All right. Now, we should also try propane. Propane is C3H. 2 times 3 plus 2. 2 times 3 plus 2 is 8. Plus O2 forms CO2 and H2O. Right? So C3H8 plus O2 forms CO2 and H2O because this is complete combustion. All right. Now let's try to work out how to balance this equation correctly. So remember what Mr. So just said. Count the carbon first. C3. If it's C3, how many H2O do I need? How many CO2 do I need? 3 carbons, so 3 CO2. All right. Next, H8. If it's H8, how many water do I need? Many students will think it's 8 H2O. But remember, 8 times 2 is 16. But you don't want 16 hydrogens, you only want 8. So you need 4. 4 times 2 equals 8. So 4 H2O is needed. The final step is, of course, to count the oxygen. And you must be very careful in doing so. All right. So the first one, 3 CO2, 3 times 2 equals 6. Plus 4 H2O, 4 times 1, 4. 6 plus 4 is 10. Do we write 10 O2? Remember, you want oxygen atoms. 10 atoms, you need 5 O2. Okay, so C3H8 plus 5 O2 forms 3 CO2 plus 4 H2O. All right, so these are the chemical equations for complete combustion for the first 3 equations. Once you have finished, can you please give me a thumbs up so I know you're done and I can move on to the last section for today, which is substitution. All right, so I think everyone is done. So remember ACS, alkane combustion, and the next one is substitution. Now, substitution should be a familiar concept to you if you play sports. Very often in sports, CCAs, during your school games, you will have to have substitutes. Why? So what is a substitution reaction? A substitution reaction is a reaction where an atom in the molecule is replaced by another atom or group of atoms. All right. So this is replacement, what we call substitution. So the first example is to substitute methane with chlorine. All right. So what happens is that methane is CH4 plus Cl2 So what do you notice? The Cl comes in and forms a bond to carbon. So what has it replaced? The chlorine has replaced hydrogen. Now, the hydrogen doesn't come out as H. The hydrogen comes out as HCl. Because remember, you had two chlorines, Cl2, right? Two chlorine atoms. One got attached to the carbon. The other one got attached to the hydrogen. All right? So which atom in the alkane has been substituted out? Out is the hydrogen. Which atom has replaced the atom in the alkene? Which atom replaced? Chlorine. All right. Next, what is the main purpose of UV light? For the physics students, you have learned a little bit about light. You should know the purpose of ultraviolet light is to provide activation energy to start the reaction. Okay, so every single reaction has its own minimum activation energy. So you need to give it light, like UV light, in order to promote that energy to you, in order to provide the sufficient amount of energy to start the reaction. And the last question for this, will the substitution just stop at one chlorine going into the alkane? Well, obviously the answer is no, right? There is nothing stopping a second molecule of Cl2 from reacting with the same alkane. This means that more than one chlorine can potentially go in, substitute hydrogen out. So we go on to the next part, which tells you this. In excess chlorine means a lot of chlorine. You will have multiple substitution. All right, so the chlorine can substitute more than one hydrogen atom. So you can see it went from chloromethane, only one chlorine, to dichloromethane, two chlorines, to trichloromethane, finally tetrachloromethane. I think tetra is what you all are not familiar with. Tetra is the prefix for 4 number of atoms. 4 chlorine, so tetrachloromethane. Now, so this is a little checkpoint. Draw the organic product when ethane, C2H6, is reacted in ultraviolet light. So ultraviolet light is a clue for you that this is substitution of alkanes. All right. Now there are two scenarios here. C2H6 plus a small amount of chlorine. Now small amount of chlorine means chlorine is limited. If it's limited, can you have so many chlorines going into the organic molecule? The answer is no. You will just favor the single mono substituted product, meaning you will just draw something like this. All right. When you have a small amount of chlorine, only one chlorine goes in. When you have a large amount of chlorine, things change. So if you were to go to excess chlorine, things change because now more chlorine can go in. So in excess chlorine, you may have even 6 chlorines going in to substitute away all the 6 hydrogen atoms that were once in ethane. All right. Now, if the question didn't state explicitly if chlorine gas is in excess or is it a small amount, we will assume this. Assume Cl2 is limiting if not stated. All right. If it's not stated if Cl2 is limiting or not, you assume it's limiting. That means If it's not stated, we just draw one chlorine going in to substitute one hydrogen. All right. Now at this juncture, have we copied down this page? If you are done with this page, can you please give me a thumbs up so now I know you're done? Okay. All right, let's move on. Now, the last part shows you what you will learn at A level. So at A level, it will build on whatever you have done at Sec 4 O level. Okay, so up to page 8 just now was O level. Now page 9 is A level. All right, at A level, you will learn the mechanism behind substitution of alkanes with chlorine. The name of the mechanism means how does the reaction happen. The name of the mechanism is free radical substitution. So what happens is, first step is chain initiation for short. So what happens in the first step, initiation, is the chlorine-chlorine covalent bond breaks. And that's why you need ultraviolet light. You need ultraviolet light to provide energy for the chlorine-chlorine covalent bond to break. That's the purpose of ultraviolet light. Now, when the covalent bond breaks, what happens? You know that a Cl2 molecule contains 2 atoms combined together. It's diatomic. Therefore, when the covalent bond breaks, you end up having a free radical. A free radical basically is a chlorine atom. Okay, a free radical is basically chlorine atom. Cl is 287. So I'm sure you know by now, chlorine's electronic structure is 287 as an atom. This means that the outermost electron shell has 7 electrons, right? So you know by now 7 electrons is actually not stable. It wants to be fully filled, but it's not, right, currently. So chlorine will do all it can to gain an electron, share an electron, all right, such that it can achieve a fully filled outermost electron shell. And that's exactly what it does in the second step. Can you see that in the second step, the chlorine starts to form bonds? Form bonds with whom? Form bonds with hydrogen first. That's why it's HCl formed, right? The hydrogen from the alkane comes out, but it doesn't come out as hydrogen atom. It comes out as HCl. The H exits as HCl. All right, it never ever exits as H. It exits as HCl. All right. Then the next step, what happened to the other poor chlorine? The other poor chlorine forms a bond with carbon. Do you notice a second molecule of Cl2 reacts with the carbon to form the product plus another chlorine radical? So what do you notice? The chlorine atom or the chlorine radical is regenerated, right? It is used up here, used up. Then is regenerated in the second step. And that's why we say it's a chain reaction. One chlorine atom is used up, but the second step, produce and regenerate another chlorine atom. So this reaction can go on and on and on and on. It will continue producing products on its own without further assistance until every reactant, the alkane, the chlorine, has run out. Why is that so? Because the chlorine radical is always being regenerated. All right. So this is what we call a chain reaction. So this is one of those commonly asked questions. Why do you think the reaction can go on and on and on? Why do you think one molecule of chlorine can destroy many molecules of alkanes? The reason is this, because the chlorine radical is regenerated in the second step. Okay? Now this reaction basically goes on and on and on until all the reactants run out. Okay? So that's called chain reaction. So that concludes set number 8, alkanes. All right, now we will continue on with our training for set number 9, alkenes, next Wednesday. Now, next Wednesday also happens to be our final training session. All right, the actual competition, as I mentioned, is on 23rd of May. It's a Tuesday. All right, so I would appreciate if you lock this in your calendar. It's a Tuesday of term 2, week 10, and it will begin at 2:30 p.m. All right, so it's after school. Now, I will be writing to all teachers with the name list of students taking part in Chemistry Olympiad. So your teachers will know to excuse you from lessons as well as CCA from 1:45 p.m. onwards on Tuesday, 23rd May. All right, Ken? So with that, I conclude my training for today. Thank you. I will stop the recording now.